All right. Hello, everyone. Welcome to VSPG. Today, we're going to hear from Professor Jeff Vervoort. He's talking about the growth of Earth's earliest crust, unraveling the isotope record. So I'll go ahead and introduce Jeff. Professor Vervoort is a leading expert in radiogenic isotope geochemistry and geochronology and has been among the pioneers in applying these tools to understanding the early Earth. He uses the hafnium and neodymium isotope record of the early Earth to help better understand its early differentiation and how this relates to the formation and evolution of Earth's earliest continental crust. Recently, one of his main focuses has been on the integrity of that isotope record, to what extent it has been modified by subsequent metamorphic events, and how we can assess whether it faithfully records original isotope compositions. Jeff uses coupled uranium-lead age and hafnium isotope analysis of zircon and uranium-lead age and neodymium isotope of rare earth element-rich phases to approach this problem. Dr. Vervoort received his PhD from Cornell University and was a research scientist at the University of Arizona for several years before joining the Faculty of Geology at Washington State University in 2002. At Washington State University, he's also director of the Radiogenic Isotope and Geochronology Laboratory. We're very excited to have you today, Jeff, so please take it from here.
All right, thanks. Can everybody hear me?
Yep, we can hear you.
So yeah, I was pleased to see a lot of familiar faces in the audience. So greetings, everyone. So what I'm going to be talking about today is work that's been going on with me for several decades, involving a number of people. The most recent of which are shown here, including longtime collaborator Tony Kemp, who figures prominently in this talk. So I start with this slide. As geochemists, we are interested in this blue marble, how it not only how it operates today, but how it formed and how it has evolved through time. But the ironic thing is that despite hundreds of thousands, if not millions, of isotope analyses and geochemical analyses, we know more about this body, the moon, than we do our own Earth. And the reason for that, of course, is that, as all introductory geology students learn, the Earth is a dynamic planet, and where we have crust constantly being created at spreading centers and then destroyed at various time scales, short time scales for oceanic crust, and longer and uncertain time scales for continental crust. So this has led to these more complex images that we have of the whole Earth, showing that no part of the silicate part of the Earth is really truly primordial and unaffected from its earliest creation. But my interest in this talk is the scum that sits on top of the mantle, the crust, and how it has evolved through time. This is a picture from Nouveau Agatuk from Jonathan O'Neill, showing what some of the earliest crust may have looked like on Earth. So I probably don't need to show this slide to this audience, but I do so to maybe make the point that despite talking and arguing about this for the last 4 decades, we probably are in no better consensus as to how the continents have grown through time than we were, back in the 80s, when a lot of these curves were first drawn. I always like to say there's 2 points that we are in complete agreement on, and that is we have 100% of present day oceanic or continental crust today, and we started out with none. But beyond that, there's there's little agreement on how we got from point A to point B. So the reason for this, of course, is that I'm sure everyone in this audience knows is that we don't have much of a geological record to work with, and this is a map shown by from Groves and Santosh, and it shows the Archean cratons, which is a small amount of continental crust. But it's important to remember that of these Archean cratons, only a small part are really Archean in age, and a vanishingly small amount are greater than 3.5 billion years old, and there are no pieces of crust older than 4 billion years, at least evolved crust that everybody can agree on. So the point is we have very little to work with. So the question is, we have no evolved crust older than 4 billion years preserved in the geological record. So the question is, did it ever exist, or was it once abundant and has since been destroyed by various mechanisms? And that's what this talk is about. So I go back to this map because it shows some of the Archean cratons that we've worked on or that I'll be talking about in this talk, and they include the famous areas from southwest Greenland, up in the Slave province, the Castor Ice complex, Nuvuagatuk on the shores of Hudson's Bay, the Wyoming craton, or the Wyoming province in the North American craton, San Francisco craton in Brazil, Zimbabwe craton, and the Capel craton in Africa, and the Pilbara and Yilgarn cratons in Australia. We've worked on many of these things, but I'll be talking about these in this talk. So I thought it'd be worthwhile to take a look through these rocks and see what this archive looks like. And many of you are familiar with this, but it's instructive, I think, to look at the rocks and how they appear in the field. So this is, of course, the Castor Ice complex, and these have the claim of the Earth's oldest rocks based on some of the early geochronology by Sam Bowring, and this famous cover slide from Geology showing this 4 billion year old rock from the Northwest Territories. But the fact of the matter is, there's vanishingly small amounts of the Acasinites that are truly 4 billion years old. Their age components 4 billion years to 2.6 billion years, with peaks at 4, 3.9, 3.4, 2.9, and 2.6. And it's overprinted significantly by the Wapme origin at 1.9 billion years. Another terrain that makes the claim of being Earth's oldest rocks is the Nuvuagatuk greenstone belt. And this is a slide I showed before from Jonathan O'Neill. And the problem here is that there's really no datable phase, at least in the uranium-lead zircon geochronology sense, to provide a robust age for these rocks. But based on samarium neodymium isotope evidence, Jonathan O'Neill and others have argued that these rocks are older than 4.2 billion years. And I'm not going to weigh in one way or the other on this, but if there was crust on Earth at 4.2 billion years, this very well may have been what it looked like. Another famous area is the Mitsoq gneisses in southwest Greenland. These are probably our best record of the oldest crust, the least complicated. and they have ages of 3.9 to 3.6 billion years. And significantly, they are overprinted at 2.7 billion years. And this is what a lot of those gneisses look like, which look, for those of us that have seen these gray gneisses in the field, we see this pattern over and over again. So a number of years ago, we had the opportunity with the NSF proposal to look at the São Francisco craton in Brazil with my student Manuela Botero and others. And these are these beautiful gray gneisses with ages 3.6 to 3.3 billion years, and significantly overprinted at 2.5 and 2.1 to 2 billion years. And so also very complicated. And Manuela's got one paper published on this and another one that should be out pretty soon. Also in the royalty of Earth's oldest rocks are those from the ancient gneiss complex with ages 3.66 to 3.2 billion years. A number of people have done excellent geochronology on these. And the Barberton Greenstone Belt with ages 3.5 to 3.2 billion years. And this is what they look like, and now what is called Eswatini, these beautiful banded gneisses. Also, a number of years ago, we had the opportunity to go to do some sampling in Zimbabwe, and the old rocks in Zimbabwe are widely exposed throughout the country, although not very well exposed in many places, but in river bottoms and that sort of thing. But they have ages 3.6 to 3.3 billion years, and also events at 3 to 2.8 billion years, and a big magmatic vent at 2.6. And this is what the rocks look like in the Tokwe River area. And these rocks have components 3.6 to 3.3 billion years. And this is also a paper in review by Manuela Botero. We also went far east in Zimbabwe and sampled a terrain that hadn't been dated very well, hoping that it would have some enclaves older than 3.5, but these turned out to be dominantly 2.9 billion years. And then finally, we have the Archean of Western Australia, the Pilbara craton and the Heelgarn craton. The Pilbara is ages 3.5 and 2.8, and is probably our best, least disturbed rock archive to work with. And we're all familiar with the domal pattern from these, showing these granitic complexes, which for those of you who have seen these, you probably know this already, but I always thought before going there that these granitic complexes were the high grounds and surrounded by the greenstone belts in the lowlands, but actually the opposite is true. The greenstones are the ones that form the ridges surrounding the granitic complexes themselves. But if you look at some of these rocks, they are as undeformed and as fresh looking as say your garden variety Cretaceous granite. And so there's a picture of one of them here with age of 3.4 billion years. Also, you see extraordinarily well-preserved pillow basalts like the apex basalt. And then finally, we have the Heelgarn craton, which unfortunately is very poorly exposed, but it has components as old as 3.7 billion years down to 2.6 billion years. But it does notably contain the Jack Hills metaconglomerate, and which of course contains detrital zircon grains as old as 4.4 billion years. And if you don't know where Jack Hills are, it's over to the right here somewhere. And if you're lucky enough, you can have this fine fellow show you to the Discovery outcrop, which is shown here. This is Tony Kemp in this photo. So, in summary, other than the Pilbara, what we see here in the geological record is rocks that are complicated, and if you have complicated rocks, these can yield complicated results. So, with these little bits of ancient crust, with arguably no intact rocks from the first 500 million years, how do we best understand Earth's early history? And of course, being a geochronologist and isotope geochemist, we do that with geochronology and isotope geochemistry. So I'm sure most everyone in the audience is familiar with this, but I throw it in because I've hit it in this talk for a while. But if we have a very simple bulk Earth, which we call the bulk silicate Earth, which is the whole Earth minus the core, and we approximate that composition based on chondritic meteorites, and that's what CHUR is, chondritic uniform reservoir. So if we melt that rock, say at 3.6 billion years, you're going to have divergent evolution where the crust will evolve towards negative or less radiogenic neodymium and hafnium isotope compositions, and the depleted mantle left over from that extraction will evolve to more radiogenic neodymium and hafnium isotope compositions. So isotope geochemists don't like dealing with small numbers, so we put things in an epsilon notation, which normalizes everything to CHUR, and it does it throughout Earth's history. And so that former diagram can be translated to look like this, where the crust evolves towards negative epsilon values, both for neodymium and hafnium, and the depleted mantle evolves towards positive values, both in neodymium and hafnium. So, and to a first order, this general model holds quite well. This is a compilation of zircon hafnium data from Bruno Dweem about a decade or so ago. And what you can see here is that you see a trend that's consistent with extraction of crust. And left over from that extraction of crust, we have evolution of the depleted mantle that corresponds to that. The same is true for neodymium isotopes, and this is a compilation done by Crustal, and I hope I'm pronouncing that name correctly. I'm not sure about that. But this is bulk rock neodymium isotope data, and in this compilation, and again, crust evolves towards negative epsilon neodymium values, and the depleted mantle left over from that crust extraction evolves towards positive values. And the reason we look at these two systems together is that they have remarkable coherence in a vast range of earth and mantle materials, from oceanic basalts to lust, to continental sediments, to xenoliths, continental magmas, you name it, they all fall along this well-correlated array, which I called the terrestrial array, with few exceptions, the exceptions being these iron manganese nodules in crust and other very metalliferous sediments that that are shown in the purple symbols here. So we tend to look at these systems in concert. But if we look at the details of the isotope record for the Archean, it's not quite so simple. And this was a compilation that Tony and I did for our 2025 paper and annual reviews. And it shows bulk rock neodymium isotope compositions published in the literature. And I've broken down here into felsic, mafic, and ultramafic. And one remarkable thing about the record is that you can see more variation, or at least as much variation, for the oldest rocks as you do at 2.5 billion years. And so that's been used as evidence that by some, that there was very early differentiation of the Earth with voluminous crustal reservoirs extracting as early as 4.5 billion years, and corresponding depletion of the mantle to go along with that. So that's what I'm investigating in this talk. And the astute observer may have noticed that Putz's compilation of neodymium isotopes falls really nicely along this depleted mantle evolution line. And this is in contrast to the compilation of the literature. So I asked him about it, and he said, well, yeah, we filtered out everything that fell above the depleted mantle line that starts at 4.5 billion years. And so that's, in my mind, self-fulfilling prophecy. So I think it's important to look at the record in detail on its own merits. So I've also done the same compilation for bulk rock hafnium isotopes. And here you can see a similar variation in hafnium isotope compositions. Particularly, I'll note for ultramafic compositions. It's been argued that these are more representative of the mantle, but they're also most clearly the most easily disturbed of these rocks. So, and there can be a lot of ways where you can have complicated systematics in these rocks, either from open system behavior, where you're moving these two elements around. You can have mixed components in your whole rocks, as is obvious from some of these slides. And the zircons themselves can also be complicated. We know that zircons are zoned in ages, and you can have older cores and younger rims, and associated with that, you could have mixed domains during the analyses, and or lead loss, from subsequent events. So, but zircon does have considerable utility in sorting out this problem. And we can do this both for detrital and magmatic samples. And this is because we can determine an age, at least for magmatic samples, relatively unambiguously with the uranium lead system. And then we can also do hafnium and isotopes and even trace elements on the same grain, and indeed on the same spot. But there's the good and the bad about zircons. I remember a talk by Jim Mattinson a number of years ago, and he said the good thing about zircon is that they last just about forever. The bad thing about zircon is that they last just about forever. And so you have to be cognizant of that, because these grains, especially the oldest ones, often have mixed age and hafnium isotope domains, and what you analyze must correspond to the uranium, lead, and the hafnium has to correspond in the analysis. So I'm going to illustrate this with a few simple slides. The only thing we can do when we're measuring hafnium isotopes or any isotopes in a sample is measure what we have today. So we can measure the hafnium or neodymium isotope composition, and we measure the parent-daughter ratio, in this case, lutetium-hafnium ratio, and that ratio controls the trajectory that we back calculate to the composition at which it's formed. But if there's a change in that parent-daughter ratio, either for lutetium-hafnium or samarium-neodymium, then all bets are off on calculating what that initial ratio was. And looking at these Precambrian gneisses that most of us have looked at, it's easy to see, how you could have a disturbance and mixed domains in a whole rock sample. The other thing that sometimes gets ignored is that in order to calculate the initial, you need to know the age. And so age controls where on the trajectory you calculate the initial. So, and for hafnium, ironically, it's the most, or hafnium and zircon, it's the most critical because of the difference between Schur and the zircon makes it for a steep trajectory. So the age controls where on the trajectory you calculate the initial. So if it's 3.5, it'd be something like this. If it's 3.6, it would have an epsilon of 0. And if it was closer to 4 billion years, it would have a highly positive value. All of these have the same hafnium isotope and lutetium hafnium compositions. The only difference is where you stop on that trajectory to calculate the initial. So our approach has been using the laser ablation split stream approach, where we do simultaneous uranium, lead, and hafnium isotope measurements. And we say the only way to make sure that you're analyzing the same zone in the zircon is to analyze the same zone in the zircon. And this was work that was pioneered by some Chinese labs, and Chris Fisher was instrumental in helping setting it up in our lab here at Washington State. And this is kind of a typical configuration where you have a laser and you ablate the sample, you create an aerosol, and you sweep that aerosol to be analyzed for uranium, lead in this case a high resolution ICP-MS, and the hafnium isotopes are measured simultaneously in a multi-collector ICP-MS. So our focus has been on the magmatic record, and we do that for a couple of reasons. One is that we can get as unambiguously as possible a crystallization age from the zircon based on the whole zircon population rather than one single grain. And then we do hafnium isotopes of the zircon, and we approach the hafnium isotope measurements just like we do uranium, lead, where we'll analyze a dozen different spots, and we determine the hafnium isotope composition from those measurements. So the first, one example I'll use to illustrate this, and the first project that we did once we started getting this going, was to look at the zircon hafnium from Southwest Greenland. Again, these are the Emitsok gneisses with ages 3.9 to 3.6 with this overprint at 2.7 billion years. And one reason we focused on this is because the published whole rock neodymium isotope data from this time was highly heterogeneous, with positive values up exceeding +4 at 3.8 billion years, and trailing off of some negative values. And so if the hafnium-neodymium isotope correlation holds for these rocks, we would expect an enormous range in hafnium isotopes from some 15 epsilon units or more. So that would be the expected range in hafnium, again, based on this correlation of epsilon hafnium, roughly about 1.5 times the variation you'd see in epsilon neodymium. So, but in fact, the data we got for these rocks over some 200 million years was remarkably homogeneous. And what's shown here is the mean value for all these, and each one of these spots represents individual analyses. So just like a uranium-lead isotope analysis, it's important to get get the mean value for uranium-lead. You just don't pick the highest, the oldest age and the youngest age, and in a laser ablation ICP-MS, and say that's the range of ages in the rock. So that's a very important point. Oops. So in comparison to the neodymium, we have an extraordinarily restricted range in hafnium isotopes. So this shows a very clear disconnect between the hafnium isotope system and the neodymium isotope system in whole rocks. So we've taken this approach to a number of different terrains, and shown here is a compilation from my paper with Tony in 2025. And you can see all the different terrains shown here on the right. And we've analyzed a number of these using the techniques that I mentioned, getting a robust uranium-lead age for the magmatic component in the rocks, and then doing a pooled hafnium isotope composition. And then we took that same approach to data from the literature, taking only samples that had a robust uranium-lead age, and multiple analyses of hafnium from those rocks. And you can see with the error bars here, what those ranges are in those rocks. And so in contrast to the whole rock record, we see a very coherent record here. I'll talk more about that later. Well, I've shown here in the background the whole rock hafnium isotope record from this same age range, also involving many of the same terrains. So in looking back at the whole rock hafnium isotope record and neodymium isotope record, even though bulk rock neodymium and hafnium isotope analyses can and do yield accurate initials, and many of these are certainly accurate, it's important to recognize that these isotope systems in these complicated rocks that we look at can also be easily compromised. And so I think taken as a whole, you can't trust the whole rock hafnium and neodymium isotope record for models of crust and mantle evolution. So our takeaway from the hafnium isotope data, is that the best constrained hafnium isotope data shows that the depleted mantle reservoir does not separate significantly from Chur until about 3.8 billion years. And this corresponds, in our mind, to the time when continental crust begins to be stabilized in significant volumes on the surface of the Earth. So, but what are we going to do with neodymium? So how do you reconcile the hafnium isotope record based on zircon with the neodymium isotope record from bulk rock samples? That has been a problem. And the approach that we're using now is to do a similar approach to what we do for uranium, lead, and hafnium isotopes and zircon, and that is using uranium, lead, and neodymium isotopes in a number of phases, such as apatite, titanite especially, and allanite. And I'll talk about that for a little bit. Hopefully, I still have some time. So a number of people have been working on this. Chris Fisher was one of the pioneers, and Johannes Hammerle has made some really important contributions, including on this slide here. And this what's shown here is samarium neodymium isotope data done by laser ablation, multi-collector ICP-MS on trace phases, apatite, and allanite. And there's also a whole rock composition, done by conventional means. This sample is a very famous Greenland sample, 110999. That's been analyzed by many different people for different purposes, probably unfortunately, because it's a complicated rock. But it has a zircon uranium lead age of 3.8 billion years with a roughly chondritic, slightly positive epsilon hafnium of 0.5 or so. And the whole rock neodymium on that is considerably positive at 3.8 billion years of 2.7 and 2.4 by two different methods. So if you look at the data here, you'll see that it forms a rather nice isochron with an age not at 3.8 billion years, but an age in the late Archean of 2.69 billion years, and with an initial for this isochron of minus 9.5. So it's clearly not 3.8. And another way to look at the data is that if you take their neodymium isotope compositions and their samarium neodymium ratios for all these phases and project them back into time, if it's been a completely closed system, then it's going to converge at a point at 3.8 billion years when the clock starts and the system starts evolving. Well, we can see that's not the case. They don't converge at 3.8, they converge at 2.7, which of course is the age of the isochron. So what this demonstrates is that the samarium neodymium isotope system is decoupled from the uranium lead age. So simply using the initial for the whole rock calculated at the crystallization age is a risky business at best. So another example of a system that does hold together was work done in the Pilbara by my student Ross Salerno a number of years ago. And again, remember the Pilbara has the benefit of having relatively undisturbed rocks. And these are examples of that. This is one sample with a zircon age with an intercept of 3.3 billion years and a mean 207 to 6 age of 3.3 billion years. It looks, for all the world other than some recent lead loss, very simple and homogeneous. The hafnium isotopes are also very homogeneous. Each one of these bars represents a separate hafnium isotope analysis by laser ablation ICP-MS. And that gives a mean of 0.8, and which agrees perfectly with the whole rock epsilon hafnium of 0.6. And so it looks like for this sample, the lutetium hafnium system has been closed since the formation of this rock. But the other thing that Ross did is to look at the uranium, lead, and samarium neodymium systematics And this is a sample with an age of 3.37. You can see in the upper left, the titanate uranium lead ages, giving a nice coherent age. And that's shown there. But we can also do, as was the case in the Hammerly paper, do samarium neodymium isotopes by laser ablation, and shown here apatite and titanite analyses yielding an isochron of 3.32, identical to the age of the titanite. And we can do neodymium isotopes, both by whole rock on the bulk rock sample. We can also calculate neodymium isotopes on the intercept of this isochron. Both are in great agreement of 0.4 and 0.6. And we can do neodymium isotopes on the trace phases. Each one of these bars here represent an analysis done by laser ablation on titanite and apatite. And you can see that they overlap within uncertainty of all the other neodymium isotope analyses. So when we take all those phases and project them back into time, in this case, everything does converge back at the crystallization age of the rock. And so this represents a closed system. So with some conclusions here, due to open system behavior, the bulk rock neodymium isotope records from many, and I would include bulk rock hafnium isotopes for that matter, earlier samples have been compromised. And I think we can show that convincingly in places like Greenland and many other places that we've now analyzed. And if we look at the best constrained hafnium isotope data, such as I showed some examples from, and what Ross has done in his work in the Pilbara, it shows that the depleted mantle reservoir does not separate significantly from Chur until about 3.8. And we think this represents the time when continental crust begins to be stabilized in significant volumes. And thirdly, neodymium isotope analysis of accessory minerals allows us to evaluate the integrity of the neodymium isotope record. When we examine data of rocks where both systems are closed, such as what Ross has done, both hafnium and neodymium agree, and there's no hafnium-neodymium paradox. So I think this is what's shown here, which I didn't point out. So here's zircon hafnium in the study by Ross, shown in these red squares. And this was his compilation of zircon hafnium, and this is compared to the neodymium isotope in whole rocks from these same samples that Ross analyzed. And you can see that they both are, broadly chondritic. So there's one last thing I'd like to close with, and that's one of the best lines of evidence in my mind for the existence of a pre-4 billion year old crust or not is looking at the detrital zircon record. And if we go to modern rivers today, such as the Mississippi, Congo, Yangtze, Amazon, we see a representation of the rocks that are exposed in that catchment basement. And we see, all these familiar peaks like at 1 billion years, at 2.7, at 1.9, and to 2 billion years, etc., representative of what are exposed in the catchment area. But all of these records kind of backstop at about 3.5 billion years, which is consistent with what is generally exposed in these areas. And so you'd think that if you went back to the oldest sediments, you would be able to look back in a time even further. So this was this great paper by Ellen Nutman in 2001, entitled The Scarcity of Greater than 3.9 billion year old zircons and greater than 3.5 billion year old metasediments. And shown here are the 3.5 to 3.6 metasediments, again backstopping at about 3.9 in this case. And here are the older sediments, again backstopping at 3.9. And so even in the oldest sediments that we have, we'd see scarce evidence of crust older than 4 billion years. The Jack Hill zircon and very few others being rare exceptions. So the other thing that's perhaps interesting to think about, if we go back to these terrains, the oldest rocks for both the evolved granitic rocks and the mafic rocks, as near as we can tell, are roughly coeval. And what this means is that the production of those evolved Bradley granitic compositions happened very quickly with some two-stage process over a short period of time. So their extraction from the mantle, happened fairly quickly, not in a single stage event, but in a rapid two-stage event. So I'll close again with this image of the flow amphibolites and mafic rocks from Nouveau Agatuk, and I'm not arguing that these are older than 4.2 billion years, but if there are the oldest rocks on Earth, this is probably what they look like. And so let's circle back on the crustal growth models. I think my opinion is that we have some delayed growth starting at about 3.8 billion years with some episodicity in it, probably related to some balance and interplay between crustal production and preservation, as Peter Kaywood and others have advocated. So with that, I will finish up a little bit early, maybe.
All right, thanks, Jeff. Great talk. We'll go ahead and switch to questions and discussion. So you can ask a couple ways. You can go ahead and type a question in the chat, and I can read it aloud for you, or you can find the raise hand button, which if you go to the bottom of your screen and click the reactions button, raise hand pops up right there. So I'll give some time for people to formulate their questions. Okay, Roger, please go ahead.
Hi, I guess I found the react button first. Hi, thanks for the talk. I guess I'm just curious if this change in the amount of mantle extraction at 3.8 can be interpreted globally. Like what assumption does one have to make about the well mixedness of the upper mantle, right? Like could it be a local change in the upper mantle composition, or can it represent all of the upper mantle?
Yeah, well, that's a great question, and I'm probably not the best one to answer, mantle heterogeneity at 3.8. But what we see throughout all these terrains is a very consistent chondritic signature, through 3.8 to 3.6, and it's not just one terrain. It's everything from Greenland to Zimbabwe to Brazil and on and on. So it seems to me that this represents, a pretty widespread signature, which then argues, for a well mixed upper mantle.
Thanks, Roger. Roberta Rednick, please unmute yourself and go ahead.
Hi, really great talk as usual, Jeff. I really enjoy listening to your very clear explanations. As you know, there's been discussion about a non-chondritic Earth based on 142 neodymium, and I'm always trying to wrap my head around that in terms of what implications would that have, if anything, for early rocks. So maybe you could address that.
Yeah, I guess with 142, there's a couple issues. There's the non-chondritic Earth issue, and I'm still a bit agnostic on that. The other issue with 142 are these very positive values that you see in some of the rocks.
Right.
Some, but not all. And in fact, it's the minority of rocks. The Greenland being the main exception that has the most strongly positive values. And the way that I'm thinking about it now is that these are two separate processes. That 142 neodymium is not representative of crust extraction, but rather differentiation of a primordial event, the magma ocean, and where we have demonstrated some different partition behavior between the lutetium, hafnium, and samarium neodymium systems. So I think of the 142 neodymium, these positive values, as somewhat of a red herring, that we're not looking at the same thing, that it doesn't represent crustal extraction, but something else.
And the non-chondritic Earth, if it exists?
Well, that would affect our baseline of what we're looking at.
Right.
Yeah, and yeah, I think that the effect on the early Earth is relatively small compared to what you have on the present day Earth.
Thanks.
Yeah, thanks, Roberta. Don Davis, please go ahead.
Excellent talk, Jeff. So the obvious question that remains is, what was the nature of the Hadean crust? What's your opinion?
I think it's a lot like what you see at Nouveau-Agatok. And, with short residence time on the surface of the Earth, obviously there was crust. I mean, nobody's denying that. I mean, and there was obviously some evolved crust. But I think, something like what we have at Nouveau-Agatok was like that. And, with some localized places where you have production of some evolved crust that have produced zircons in some places. But yeah, I think that's kind of what it would look like. What's your opinion?
Well, how about anorthositic crust?
Yeah. But where are those zircons?
Well, yes, obviously you have to have local areas where hotspots or something like that are generating zirconiferous rocks. But anorthositic crust would eventually subduct once the base of it get converted to a thick enough layer of garnet as the temperature profile of the Earth gets lower. So at some, well, assuming that we know that the moon had an anorthositic crust, so there's no reason to believe that the Earth didn't have it as the primordial crust. The question is, how long did it last? And once it became heavy enough, it would totally subduct and be replaced by oceanic crust, presumably. And 4 billion years looks like a good enough time for that to
Yeah.
occur. Mm.
Thank you.
Anyway, great talk. It was
Well,
very
thanks.
clear.
All right, Roberta, you jump
Yeah,
back in.
I just wanted uh, to offer a comment about a north acidic crust. We have to remember that the moon is much smaller body than the Earth, and so plagioclase is stabilized much deeper into the planet than
Mhm.
on Earth.
That's right. Yeah, yeah.
So I'm not sure we can necessarily conclude that we had a north acidic crust. I mean, I like to look at Venus as an analog for early Earth,
Yes.
full of basalt and maybe other things.
Yes, and Venus lost its water, which was the only difference, basically. So it didn't have plate tectonics anymore, and a static lid. Yeah.
Cool. Yeah, with these kind of conversations, I'm noticing there's certain people who, if they were in the audience, would be having a blast. But probably had to miss today. Cool. So we'll give another few seconds for people to speak up if they want. No need to raise your hand. All right. Well, great, Jeff. That was a really, really good talk. Thanks so much. Thanks for participation from the audience.
Yeah, well,
And
thanks for inviting me, and yeah, it's a privilege to be able to give my side of the story here.
it was a
Thank
great
you.
contribution.
Mhm.
Well, all right, everybody. Take care till
Bye-bye.
next time.
Bye-bye.
Thanks, Jeff.
Bye-bye.
Bye-bye.